The Westland Wyvern was one of the most unusual aircraft of the post-war years. It was designed to use both piston and turboprop engines, and had a bold look to match its ambitious design. In this video, we're going to take a closer look at the Wyvern's design, how it was structured, its wings, the engines, and more. If you haven't seen my earlier video on its development, there's a link in the description below. We will cover the three types of Wyverns: the Wyvern TF1 with Rolls-Royce Eagle piston engine, the Clyde-powered Wyvern TF2, the Python-powered production Wyvern S4. The latter two engines were both turboprops. The Wyvern's fuselage measures around 12 to 13 meters in length across these variants, with the turboprop versions being slightly longer. The fuselage featured a distinctive humped design, with the cockpit positioned high to provide the pilot with excellent forward visibility. According to a Western document, the minimum downward view angle was 10 degrees, which was an impressive figure. For comparison, the Sea Fury had a figure of 8 degrees. This kind of excellent visibility was particularly useful for carrier operations, but the raised cockpit also increased the aircraft's frontal area, which added aerodynamic drag. The fuselage structure was of light alloy stressed skin construction. It was divided into three sections: the engine mounting structure, the center fuselage with an integral wing center section, and the rear fuselage with an integral fin. For the Clyde and Python-powered versions, their fuselage depth was increased to accommodate the exhaust tailpipe beneath the cockpit. Early Wyvern models featured a one-piece stiffened bubble canopy with a faired windscreen. A possible advantage of the faired windscreen is a slight gain in performance on account of the better shape of the canopy, but the definitive version adapted a flat windscreen with a wiper. I personally think this might be because of flat version's overall better visibility, especially in heavy rains. The finalized S4 also introduced a canopy with a larger framing structure to improve structural integrity. The Wyvern's wings used a NACA 65214 section, designed as a so-called laminar flow airfoil. The main wing structure consists of a center section and two outer panels. The center section had 3 spars, while the outer panels each had a single spar. For Eagle-powered Wyverns, the main radiators were mounted behind the main spar, with the space above occupied by the inner gun ammunition tanks and inner wing fuel tanks. The outer gun ammunition tanks were positioned behind the spar in the outer wing panels, and the turboprop versions had the radiators deleted due to the nature of their engines. Wing folding was hydraulically operated and electrohydraulically controlled from the cockpit. The early versions were capable to fold wingtips as well, but the late production Wyverns removed this feature. The undercarriage retracted inwards, bringing the outer doors with it, while the inner doors enclosed the wheelbase and acted as uplocks. The ailerons were spring-tap operated to reduce pilot input force. The two-piece young man style flaps had 3 positions, interconnected by a torque tube and actuated by delta jacks. On the S4, new air brakes installed on the upper wing surface operated in conjunction with the outer flaps. To prevent aileron twitch when the air brakes were deployed, airflow barriers were fitted later. The Wyvern was armed with 4 Hispano Mark V 20mm cannons, each with 300 rounds. The belt feed mechanism was the compact Mark VII system developed by Martin Baker, which avoided the bulky roller feed mechanism seen in early British fighters like the Spitfire and Tempest. These rollers had large diameter and tend to force aircraft manufacturers to create blisters on wings. On the Hawker Tempest, these blisters were estimated to reduce speed by 8 to 10 miles per hour, which was a rather notable performance penalty. The Wyvern's tail design evolved throughout its development. Early models had a small tail fin and rudder, but test flight, especially those on the Python-powered versions, revealed stability issues. This led to the introduction of larger tail assembly on the Python-powered TF2. which was retained on the final S4 model, but with a revised horn balance design. The tailplane was also enlarged, starting with the Mark II variant. The S4 incorporated additional fins to mitigate rudder lock issues, as discussed in my previous video. The Eagle-powered Wyvern had a maximum internal fuel capacity of 431 imperial gallons across 8 fuel tanks. The main tanks were located beneath the cockpit and behind the pilot's seat, with additional tanks in the wings. With the switch to Python engine, the shorter engine length allowed the addition of a 105-gallon tank in front of the cockpit, but the introduction of jet pipes necessitated the removal of 2 forward fuselage tanks, and the capacity of the center fuselage tank shrunk to 67 gallons. The deletion of the wing radiators enabled an increase of 9 gallons per inner wing tank, while the rear fuselage tank was expanded to 105 gallons. These modifications increased the Wyvern S4's internal fuel load to 526 gallons. On the other hand, the exact maximum fuel capacity of the Clyde-powered Wyvern remains unknown, but it was likely similar to the Python version due to the identical tank layout. All Wyverns had a transfer-type fuel system, with the main tank acting as a collector from which fuel was delivered to the engine. The Wyvern could also carry 2 90-gallon drop tanks to further extend its range. Now, let's talk about weight. The Wyvern's fuel loading could be adjusted depending on the mission. A 1948 Western Technical Archive indicates that the Wyvern TF-1 could carry 340 gallons of fuel for short-range fighter missions, or be fully fueled for long-range escort or strike missions. With all tank filled, the Wyvern TF-1 weighted about 20,150 pounds, which is rather heavy for an aircraft of its type. For the Python-powered S4, the loading documents for one of which, WL885, suggested a fully fueled takeoff weight of approximately 21,573 pounds with 516 gallons of fuel. The Clyde-powered VP120, when carrying 280 gallons, had a standard takeoff weight of 15,900 pounds, but this measurement excluded 4 Hispano cannons, and the document didn't mention any ballast compensation. So if we factor in the guns, magazines, and the weight of the ammunition, the estimated combat takeoff weight with full 526 gallons of fuel could be around 18,900 pounds. So the Clyde-powered version was clearly the lightest, likely due to Clyde engines' more compact and lightweight design, which was also resulting a smaller engine cowling and reduced structural weight. So now let's talk about the engines. The Wyvern's initial power plant, the Rolls-Royce Eagle, was a liquid-cooled piston engine in an H24 configuration, featuring sleeve valves and a 2-speed, 2-stage supercharger. Initial estimates suggested that Eagle could produce up to 3,560 horsepower at 6,000 feet and 3,260 horsepower at 18,000 feet with 18 pounds of boost. However, test bench results indicated it only achieved around 3,300 horsepower with 20 pounds of boost. The Eagle was a very big and heavy engine. It had a dry weight about 3,900 pounds, which is a lot more than the similarly configured Napier Sabre 7 engine, which weighted just around 2,540 pounds dry. Now, the Eagle did outperform the Sabre 7, especially at the high altitudes, but honestly, I personally don't think the extra power was enough to make up for the huge 1,500 pounds weight difference, especially for an aircraft designed to operate mostly at medium to low altitudes. The Sabre was also much more compact. By April 1946, it was already delivering 3,000 horsepower in flight. It was also capable of producing 300 and 500 horsepower with a 20 pounds boost, but as far as I can tell, there's no solid evidence that this rating was ever tested in flight. On the Wyvern TF1, the semi-annular oil cooler was mounted in the nose, with the carburetor intake positioned just below the propeller. The radiator was placed under the wings, with the heat exchange coils mounted at an angle which was likely to minimize the space occupied by the radiators and allow for fuel tanks to be placed above them. The next power plant was the Rolls-Royce Clyde turboprop, designated as the RB39. Weighing about 2,800 pounds and producing a maximum dry output of 3,020 shaft horsepower, the Clyde featured a 9-stage axial flow compressor, a single-stage centrifugal compressor, and 11 straight-flow combustion chambers. On the Wyvern, it powered a 6-blade contra-rotating propeller manufactured by Rotor. The engine's widest section at the combustion chambers had a diameter of approximately 46.75 inches. Its air intake was positioned at the front of the axial flow compressor. Overall, the Clyde's compact design allowed Westland to mount its oil cooler beneath the engine, which created a very clean installation. Later in development, a water methanol injection system was fitted to the Clyde, which increased power output to an impressive 4,230 shaft horsepower on test beds. The engine was cleared for operation at 500 miles per hour at sea level on full throttle. However, no records confirm that water injection was ever tested in actual flight. And at last, the definitive production model, the Wyvern S4, was powered by the Armstrong-Siddeley Python 3 turboprop engine. The early Python had a dry weight of about 3,140 pounds and produced 3,670 shaft horsepower. According to Flight International magazine, the Python 3 engine used on the S4 was even heavier, which sits at around 3,450 pounds. The Python featured a 14-stage axial flow compressor, 2-stage turbines, and 11 combustion chambers. It drove an 8-blade contra-rotating propeller, also made by Rotor. If you compare the Python-powered Wyvern with the Clyde-powered version, you will notice the Clyde version had a much narrower nose. This is due to Python's reverse flow design, in which air flows 180 degrees forward through the compressor, then does another 180 degrees backward through the combustion chambers before exiting through the turbines. This layout resulted in a rather bulky midsection, with the air intake positioned towards the rear of the engine. With this layout, Armstrong-Siddeley had to design an annular air intake duct around the engine, which increased the installation's overall diameter to 54 inches. Westland had to adapt the engine size by relocating the oil cooler to the wing root leading edges. Although the Python could produce 3,670 shaft horsepower compared to Clyde's 3,020 shaft horsepower, its power-to-frontal area ratio was already inferior. Consider the Clyde could produce over 4,200 shaft horsepower with the water injection system. This performance difference would be day and night. And more critically, early Pythons had a slow throttle response, which was critical for carrier-based aircraft. The Wyvern S4 achieved operational status with the Python engine, but it's always tempting to wonder how different things might have been had the Clyde been fully developed. With its lighter weight, cleaner installation, and more power, a Clyde-powered Wyvern could have been a far superior naval fighter. That concludes this video on the design of the Westland Wyvern. I know I originally planned to cover this performance analysis here as well, but I kept expanding the content to the point where 2 videos are needed. So in the next video, we'll compare the Wyvern's performance to the best naval fighter of its time and see if it truly had what it takes to be a competitive torpedo fighter. Stay tuned.